For example, inside epsilon x, epsilon s. This one is defined by kappa y, kappa y. Actually, kappa is radius of curvature is defined by 1 over rho, and it is defined by bending moment over ei. By applying this formula, we can calculate sigma or some more relations between various physical component. And when you extend this one, then kappa is what? 1 over rho, and that's why minus y over rho is available. Epsilon x is derived by minus y over rho, and normally sigma x equals what? E epsilon x. E is of course modulus of elasticity, and in this case, when you substitute epsilon x minus e kappa y, that's available. Or finally, frequently we use the relationship. The relationship is sigma equals stress under stress. This kind of stress is defined by moment is divided by section modulus S. Okay, actually this formula is frequently used for finding stresses inside beam. When the bending moment is known, and or when section modulus is given, then we can calculate maximum stress inside. Or when bending moment is known or allowable maximum stress, then we can calculate section modulus S. Vice versa, we can calculate it. And now let's think about S, section modulus S. Section modulus S is actually defined by moment of inertia. Moment of inertia is divided by the length c, and moment of inertia I equals integral a y squared dA or something. Okay, in this case, when you think about this kind of rectangular beam and B and we can say H, then this kind of beam element, cross section, then moment of inertia is calculated by 1 over 12 BH3, and section modulus is calculated 1 over 6 BH squared. That is calculated like this one. Well, when you think about this kind of circle, the diameter is d, cross section is circle, then we can say I value is 5 over 64 d4. Actually, in this case, unit is meter exponential 4. That's the unit. Well, section modulus in this case is 5 over 32 d3. When you calculate moment of inertia and section modulus, and the relationship between moment, section modulus, and stress can be defined by this formula. Later on, when you think about problems related to bending, especially when you try to find the stresses inside the beam, then we can apply this formula frequently. Or some other relationships. or this kind of moment of inertia or section modulus can be easily applied to there. Okay, now let's think about an example. In this example, we have a beam. In this beam, on the left side is a hinge condition. On the right side, we have roller condition. If externally moment is acting like this one, the beam element is changed like this kind of shape. Of course, the dimension, this dimension L and H is given. Compared to L, H is relatively small. That means a slender beam element we can assume. Okay, when you think about in this direction is X. This direction is X. Let's say this direction is X. And this direction is Y. Let's think about that. When you introduce like this one, then the value epsilon x direction strain is given, and some other factor from neutral surface to bottom is also given. It is fixed. And our goal is to find radius of curvature and change of deflection in at this point. Okay, when you think about this problem again, we have a beam element and applied moment, and it is changed like this one, the shape, and we would like to calculate the deflection, the change in the middle. In order to find that delta value, in this case we would like to calculate delta and radius of curvature and curvature. At first, let's think about radius of curvature. And radius of curvature rho equals minus y over epsilon x. We can apply this formula. And y value is given, and epsilon is given. Y is given and epsilon is given. Two values are given, then we can calculate this one, rho. When you know rho value, that's radius of curvature, and curvature is 1 over rho. Then we can also calculate this kind of kappa curvature. Next, we would like to calculate delta value. This delta value. When you think about this big triangle, a large triangle, and the radius is rho, and this distance, this one is what? Rho minus the radius minus, and let's say this one is theta. Let's include this one is theta, and rho minus rho cosine theta, and rho is 1 minus cosine theta is available. That's the delta value. And next, when you know the theta value, then we can find delta. In order to find theta value, then we can calculate sine theta. Sine theta is what? Sine theta is sine theta. L over 2 is divided by over rho. If you know the L value is given and rho, we calculate it like this one, and finally we can calculate theta value. theta value. Theta value. If you know theta value, then the theta can be substituted there, and finally you can find delta value. I would like to summarize, repeat again this example. We have a beam element, and some externally moment is acting like this one. The shape is changed, and given condition is like this one. This kind of condition is given, and epsilon x directional strain is also given. The distance y, neutral surface to bottom is given, and we would like to calculate radius of curvature and the change, this value we would like to calculate. At first we apply this formula, and both of them we know that, then rho is available. And we apply this formula, then curvature we can calculate. The delta value is what? When you think about this kind of triangle, the radius minus rho cosine theta equals like this one. And in order to find theta value, we can calculate sine theta. Sine theta is like this one, and rho and L over 2, this distance L over 2 is considered. Then we can calculate here theta value equals sine L over 2 over rho. Then we can calculate theta. When you substitute this value to there, and finally we can calculate delta value. Okay, now let's think about another example. In this example, we have a drum. It's a cylindrical drum, and around the drum, we have very high strength steel wire is bent like this one. It's like bent this one, without any room. It is perfectly contact like this one. Of course, this steel wire has diameter D. D is given 4 millimeter, and drum radius is 0.5 meter, and that means 500 millimeter. And modulus of elasticity of the wire is given 200 gigapascal, and maximum. Okay, now let's think about an example 5.2. We have a cylindrical drum like this one, which has radius R0. R0 is given 0.5 meter, and that means 500 millimeter, and high strength wire is bent like this one. Without any room, it is well contacted around drum. And of course the wire diameter is given 4 millimeters, and the modulus of elasticity of the wire is given like this one, 200 gigapascal, and maximum allowable proportional limit is 1200 megapascal is given like this one. Okay, in this condition, with this condition, we would like to calculate the moment, bending moment, which is acting bending moment and bending stress related to this wire. Okay, in order to find bending moment, at first let's consider about a formula. Kappa equals radius of curvature is radius curvature is rho, and m over EI, and we can apply this formula. And another one, maximum allowable sigma equals moment is divided by section modulus. Okay, I value moment of inertia. In this case, I equals 5 over 64 over 4, and section modulus S equals 5 over 32 d3. With this kind of relationship, we can apply in this case. Okay, first let's think about moment. In order to find moment, then E modulus of elasticity is given, and I is calculated by this formula. And when you know rho value, radius of curvature, then you can calculate moment. Then in order to find rho value, when you think about this one, radius r 0 plus the diameter, half diameter is considered. This one is rho. Then we can calculate m equals moment, m equals ei over rho. Then rho is what? Rho is this value r0 plus d over 2, and E, let's say I equals 5 over 64 d4. Then we know everything, r0 and d and etc. We know that. We can calculate this kind of one, and m value we can calculate. M is known. Next, if we know m value, we can apply sigma value there. And finally, maximum we can calculate sigma max is available. Okay, in order to find maximum sigma value, and m over s is what? 5 over 32 d, like this one. And when you substitute this one, then let's say equals 5 over 32 d3 1, m equals r0 plus d over 2 e 5 over 64 d4. Okay, we can delete this one. D, and 5 is deleted. And finally we can summarize. 32, maybe this one is also deleted instead of 2. Okay, then 2 is go down there, 2 r0 plus d, 2 r0 plus. When I summarize it, sigma equals finally 2 r0 plus d and e d. And this one is what? Sigma maximum value. Okay, r0, d, e, d, everything we know that. And finally, we can find sigma max value. I repeat this example again. The given condition is like this one. We have a drum like this one, and outside wire, cylindrical wire. Cross section is circle, and diameter is given like this one. R0 is given like this one, and modulus of elasticity is also given. Maximum allowable value is like this one, and we would like to know maximum bending moment, and stress is related to bending moment. we can apply this formula. Kappa curvature can be calculated by this formula, and the sigma also can be calculated like this one, and the moment of inertia and the section modulus can be calculated like this one. And in order to find kappa value, not kappa, m value first, we can apply this formula. And then if we know rho value R0 plus this one is available, when you substitute there, then we can have this kind of relationship. Then we can find m. Next, we can apply this formula. M over S section modulus is like this one. And when you substitute this one there, then finally we can find sigma maximum.